Hi everyone. In this video we're going to be starting our discussion of electric potential energy and voltage, and later on we'll go on to talk about capacitance. So in this video in particular we're going to be focusing on electric potential energy, and we're going to begin by going back to think about gravitational potential energy. So if you remember, this is what we had when we studied gravity. The expression U equals negative G MEM over R. And we said that ME was the mass of the Earth, and the negative sign in this expression means that the two objects, in this case the Earth and some other mass M, which is separated by a distance R, that they are attracted together, that there is a force this way. And that's important. Those forces are equal and opposite because of Newton's third law. And this is our expression for the potential energy of the system of the two masses. So it turns out that, like gravity, you can write an expression for electric potential energy, and we sometimes just call that U. And if you have just one charge, or a pair of two charges rather, the potential energy is Q naught over R. And K, of course, can be written as 1 over 4 pi epsilon naught, Q naught over R. Notice that this is different from the force, because the force is Q over R squared. And this is also different from the field, because the field is KQ over R squared. So towards the end of this presentation, later on in this PowerPoint rather, we'll look at all of these different expressions. So this expression for potential energy, well, let's think about the sign. If one of the charges is negative, then we're going to have negative potential energy, and that's exactly what we had with gravity. Gravity just happened to be always negative, so negative G over R. Just clean that up. And gravity was always negative because the force was always attractive, but electric potential energy is negative if one of the two charges is negative. And it's going to be positive if the two charges are either both positive or both negative. So, what do you do if you have a collection of point charges? Well, you just have to calculate the electric potential energy between each pair of charges, and that allows us to calculate the potential energy of the system. Now with masses, we typically just did two objects in the system. But now it could get more complicated. For example, if we had three charges, Q1, Q2, and Q3, you would have to do a sum. So here's K, and if you distribute that, it's basically K Q1, Q2 over R12, K Q2, Q3 over R23, and K Q1, Q3 over R13. Now whether or not these would be positive or negative would depend on whether the charges were positive and negative. And just note that mathematically speaking, if you have n charges, you're going to have n factorial over 2 terms in this potential energy equation. Okay? So if I have 4 charges, then I'm going to have even more terms. Okay? But for example, I don't need to do K, Q2, Q1 because I've already done Q1, Q2. So I don't count them twice. All right, so for example, here I have 3 charges, negative 1 nanocoulomb, 3 nanocoulombs, and negative 7 nanocoulombs, and they're arranged in a line at x equals 0, x equals 1, and x equals 2.0 meters. Okay, so I have negative 1 nanocoulomb here, I have plus 3 nanocoulombs here, and I have negative 7 nanocoulombs here. And I want to find the electric potential energy of the system. So I have three terms, okay? Let's rewrite that. I'm going to have my 1 over 4 pi epsilon naught. And then if this is Q1, Q2, Q3, okay? I'm basically going to have Q1, which is -1 nanocoulombs, Q2, which is 3 nanocoulombs, over R12, which is 1 meter, plus Q1, Q3, over Q13, which is 2 meters, and then I'm going to have Q2, which is 3 nanocoulombs, Q3, all over R23. So I'm just basically putting into numbers what you had in the previous slide. So if we crunch this out, we're going to get this term is basically 3 times 10 to the -18th. This term right here is going to be 3.5 times 10 to the -18th. And this term is going to be -21 times 10 to the -18th. So if we take all those and add them up and multiply by 1 over 4 pi epsilon naught, let's just do that real quick. So we're going to get a total potential energy of the system of about -1.3 times 10 to the -7th. And the units for energy, if you put everything in meters and coulombs, is going to be joules. Now the negative sign does show that the -7 nanocoulombs is probably having the bigger effect on things. And especially because the 3 nanocoulombs is close to it. Okay, so let's take a moment to go back and think about conservative forces again. And the first thing to point out is that the electrostatic force is also conservative, just like gravity. So what does this mean? And what does it mean to have a conservative force? Well, there's three things. First of all, there's path independence for work. So it doesn't matter which path I take to get from point A to point B if I have a charge. It doesn't matter if I take a loopy path or a straight path, the work is going to be the same. Okay? So if this is path 1 and path 2, the work on 1 is equal to the work on 2. That's what that first point means. Secondly, the work along a closed path is 0. So the work on a closed path, now this can be a line integral or a surface. Right now we're just thinking about a straight line, but the work, okay, the sum of the dW's will be equal to 0. Okay, so that's integral of f dot dr, if you remember that from way back when. And the work is related to the potential energy change. Remember that work is equal to a negative change in potential. So the work done by the electric force is negative change in UE. So here's an analogy with gravity to think about first of all. Okay, so imagine that we have a vertically downwards gravitational field, kind of at the surface of the Earth. And we have a mass right here. Okay, and it's a positive mass because we're not really talking about negative mass. It's going to experience a downwards force Fg. It's going to go with the field. When it moves down, gravity does positive work because the displacement is parallel to the force. However, the potential energy of the object decreases because its height h above the ground is decreasing. Therefore, the work done by gravity is the negative of the change of potential energy. Potential energy is decreasing, so it has a negative sign for the change, and the work is positive because D is parallel to FG. Now think about this in terms of charges. Okay, here's another constant field, right? My ground got cut off, but my ground is like right there. So I have a charge, and for now, this is a positive charge in this electric field. So if we have a positive charge placed in this constant downwards electric field, the charge feels a force in the direction of the field. That's the definition of what a field is. And as it moves, its potential energy decreases as the work done on it by the electric force is positive. So again, the displacement is downwards and the force is downwards, so the work is positive, and the change in potential energy is the opposite of that. So as the positive charge moves with the field, it's actually decreasing its potential energy. Here's another way to think about this. What if we have two opposite charges? So let's say I have a positive charge and I sort of tie it so it's a certain distance away from a negative charge. It's going to be attracted. Positives and negatives attract. So if I cut this string, it's going to rush downwards, and the potential energy that it had will be converted into kinetic energy. And if you think about this, the electric force is doing work because the force is this way and the displacement is also down. So positive work is done, which increases kinetic energy from the work energy theorem, and we have a decrease of potential energy. Okay, now if you have two positive charges, it's the same situation. The charges would be repelled, and again, the potential energy would decrease as the kinetic energy increases. So this charge would be moving to the right, and we can just think about one of the charges. The same would be true of the other one. So because D and FE are parallel, work would be positive, which means that you have a positive change in kinetic energy, and U, delta U, would be negative. So it's kind of like a spring that we've squished together, and that spring is going to rebound if we cut it or get rid of it. Okay? Now, to turn this into math terms, we can calculate the work done by the electrical force moving a charge Q from point A to point B. And the expression for the work done by the electric field can be written two ways. If the field is constant, then you can simply write the work done as force times change in displacement. Okay? Now the force is equal to QE. The electric force is equal to charge times the field. So that means that the work done is QE delta R. But again, this is where the field is uniform, like in our example of a positive charge moving downwards in a field. All you need to know is the amount of charge, the value of the field, and the distance that it goes. If it's not a uniform field, then we just take an integral. And what happens is that the electric field will have a different value at every location, and we take the dot product of that field with dr. Now, the important thing about this is that just like gravity, work is only done when we move from A to B. Work is only done by the component of E parallel to our motion. So for example, if I have a field which is pointing this way, but I have an R which is pointing down, well, I don't care about the entire field. I just need the part of the field that's parallel to R. That's why we have a dot product. And because work is equal to the negative change in potential energy, this means that potential energy can be written as followed. The change in potential energy is negative QE delta R, again for a uniform field, so these two go together. And we can write an integral when it's not uniform. So delta U is equal to negative Q integral from A to B of E dot dr. And those are vectors. Okay, now the next concept is electric potential. Now electric potential is simply defined as the amount of potential energy that we have per unit charge. So we'll get more into this a little bit later when we talk about circuits, but for now we're going to just think of electric potential as potential energy divided by charge. Or if you have a change in potential energy, you have a change in electric potential. This term right here is called the electric potential difference. Now the electric potential difference is also called the voltage, and we'll come back to that. So electric potential is just what you have at one point. Okay? Kind of like you can have an electric field at one point, but in order to have an electric potential difference or a voltage, you have to go from point A to point B. Okay, now also if you have a changing electric field, you have to integrate. So delta U, as previously, was negative Q integral of E dot dr, and this is really important. The Q's are going to cancel here, so V is equal to negative integral of E dot dr. Now, why is this important? Because if you think about it, this is almost like work. Work is negative integral, it's almost like change in energy. Negative integral of F dot dr. So it's kind of a similar thing, because that's equal to the opposite of work. Remember, delta U is equal to negative W. Okay? So we'll be coming back to this, and there's actually another way that we can write this equation to solve for E if we know how V is changing. So we'll come back to that. But let's do a couple of quick examples. So a proton is accelerated through a potential difference, delta V, of negative 20,000 volts. What is the potential and kinetic energy change of the proton? And how much work did the electric field do on the proton? Okay, well, we want to go back to our definition of what potential difference is, and potential difference is change in potential energy per charge. So that means that delta U is just going to be Q delta V. So it's 1.6 times 10 to the negative 19th coulombs times negative 20,000 volts. Now by definition, a volt per meter is the same as a Newton per coulomb. Okay, and we'll talk more about this a bit later on, but that means that also volts is joules per coulomb. Because notice that if I multiply here, volts is newtons times meters, which is joules, divided by coulombs. So that means that joules is coulombs times volts. So this does give me a potential energy, which is in joules. Okay, now this is negative 2 times 10 to the 4th. So if I just think about it this way, I don't need a calculator. That's negative 3.2 times 10, to the negative 15th joules. Okay, how much work did the electric field do on the proton? The negative of the change in kinetic energy. Change in potential energy. That's 3.2 times 10 to the negative 15th joules. And I was thinking ahead of myself because what's the change in kinetic energy? It's equal to the work done. Okay? So delta U is negative 3.2 times 10 to the negative 15th, and K is 3.2 times 10 to the negative 15th. One more example. Okay, how fast is a 2 MeV alpha particle moving? And what potential difference is needed to stop this alpha particle? Now, an alpha particle is just a helium nucleus, which is basically 2 protons and 2 neutrons. So it's got a charge of plus 2e. And it's got a mass of 4 times the mass of the proton, which is 1.67 times 10 to the negative 27th kilograms. That's just one of those things that sometimes you memorize as a physics teacher. Okay, so we want to know how fast it's moving. Now the 2 MeV is actually a kinetic energy. And MeV is electron volts, which is 10 to the 6th eV. So 1 MeV is that. Okay? Now, what's an EV, an electron volt? Well, remember that we said earlier that delta U is equal to Q delta V. Okay, well that's a unit of energy. So if you take E and then volts, that's EVs. Okay, so in order to convert this to joules, what you have to do is basically divide this, you have to multiply this by 1.6 times 10 to the negative 19th joules in 1 EV. So that's going to give us basically 1.6 times 10 to the negative 13th joules. Okay, now we have 2 of those, so we have 3.2 times 10 to the negative 13th joules for this alpha particle. So that's its kinetic energy, but that's also equal to 1/2 mv squared. Now m is just this number right here, 4 times the mass of a proton. And so if we plug and chug through this, we are going to get a pretty big number for the speed. So this is a speed of about 9.8 times 10 to the 6th meters per second. So that's a couple percent of the speed of light. So it's moving pretty fast. Now, what potential difference is needed to stop the alpha particle? Well, in this case, what we want to do is use delta U as Q times delta V, because we want to take away all of its energy. So delta U is going to be 2 MeV, and then Q is just going to be basically 2E. Okay, so that means that the potential difference is going to be basically 1 times 10 to the 6th volts, 1 million volts. Okay, so this video was a bit long, so thanks for sticking with me here. Next time we're going to start talking about how voltage is related to electric fields.